The last time we talked about braze joints and mentioned that they're stronger in tension due to contact strengthening. It turns out that one thing I really didn't talk much about when we were doing soldering was kind of plumbing type soldering. And one of the problems today is they've gone to tin silver alloys for soldering joints. I did mention once upon a time in here that one of the requirements for water systems is keep the lead down. So they passed legislation about 15 years ago, essentially removing lead solders from potable water systems in homes, which is sort of interesting if you start thinking about the size of the joints and how much lead would be exposed to the water, given the fact that back in the 1800s they had lead pipes for your potable water, okay, in homes. You had a lot more contact with lead when the whole piping system was made out of lead than you do with the copper pipes today. But nonetheless, people were very concerned about the lead. And so 15 years ago or so, they legislated lead out of plumbing systems. One of the advantages of lead tin is it tends to be able to fill not only very thin gaps, but fairly thick gaps. So you may have a 1/1000th inch joint, and lead tin will flow into that without too much difficulty. You make a good joint. You could have a 5 or even 10,000th inch thick joint, and lead tin will fill that without just flowing out. Well, there are certainly other alloys that can be used, and typically people are using now tin silver or tin silver copper. So this is like 95% tin and 5% silver, and sometimes they put a little bit of copper in there. One of the problems is it melts at a higher temperature, but that's not that big a problem when you're just soldering copper in a basement or something. The problem, though, is tin flows very well. Tin, as a liquid metal, has a very low viscosity, and it doesn't want to stay in these thicker joints, and it just kind of runs out. Back in the old days, a plumber could solder up, 100 joints in the system, and then pressure test the system, and 9 times out of 10 or 19 times out of 20, they would end up with absolutely no leaks in the system. Today, if you talk to plumbers who now are forced to use the tin silver alloys, if they have to solder up 100 joints in the system and they go to pressure test it, they expect to find 3 or 4 leakers. And it doesn't matter how good a solderer they are, the solder just doesn't stay in the joints. It tends to flow out. And I mean, part of that can be corrected with better technique, but nonetheless, there are certain advantages to lead tin that have kind of kept it in use. However, it's also true that you can get the lead out if you need to. Today I wanted to start us into fusion welding, and all the things that we talked about before, we basically said there's 2 fundamental problems in bonding, and that's surface roughness and surface contamination. And the various things, cold welding, use shear and mechanical abrasion basically to get rid of the surface roughness and the contamination. Solders and brazes use flux to get rid of the contamination and interpose a liquid to get rid of the surface roughness or to accommodate the surface roughness. Diffusion bonding, of course, used heat to kind of collapse the asperities and to diffuse away the contaminants and things. In fusion welding, you're basically doing the same thing, but we're not going to talk about that as much. In fusion welding, you use a liquid between the 2 surfaces to take care of the surface roughness in all cases, because in fusion welding, by definition, you're melting something. But you also will either dissolve away or float away the surface contamination. For things like iron and titanium, the molten iron and titanium dissolve all the contamination. Doesn't matter whether it's oxygen or nitrogen or sulfur or whatever on that surface. Basically, iron and titanium and most of the nickel to a certain extent dissolve away the contamination, whereas things like aluminum and magnesium, you'll float away the contamination as a aluminum oxide or magnesium oxide on the surface. So fusion welding takes care of those same 2 limitations, but essentially we're just melting two things together. And so it's not as useful in fusion welding to start thinking about what are you doing in terms of getting rid of surface roughness and surface contamination, because it's kind of inherent in all the different processes. Now, if I want to start looking at fusion welding, you can go back to some very basic physics and say, for a typical metal, how much heat intensity does it take to cause melting? And it turns out that for a typical metal, you cannot get melting with a heat intensity on the surface. This is heat intensity in watts per square centimeter. You cannot get melting if you have less than 100 watts per square centimeter. And I can show that to you very quickly here. I'll do another demonstration probably next week. But if I look at something that's an air methane flame, that would be basically something like a Bunsen burner or a propane torch. And that will give me about 100 watts per square centimeter. So I just happen to have a propane torch. And I have a piece of steel, nice small piece of steel, so that if I can melt it, it will melt. I put it right in the middle of the flame, and if I wait a few seconds, it will start to eventually turn red. It's starting to get red now. I don't know if you can probably see it now. See it starting to turn red? I can leave it here as long as I want, and I just reached the limit. It's now radiating heat away as fast as I'm putting it in. As it gets redder and redder, there's more and more radiation heat loss, right, from the metal. I could do it longer, but if we do it too long, they're going to learn that I'm doing this. Physical plant ever learns that I'm lighting torches in the classroom. Anyway, they'll get upset. In any case, the point is, at 100 watts per square centimeter input, you end up getting to the point where when things start getting red enough, they start radiating the heat away or conducting it down the thing, although that one's so thin that the heat conduction loss out the ends is a relatively small fraction compared to the center. I was getting a reasonably wide heat zone compared to its length. So it's not really conduction, it's really radiation, but most metals melt at a high enough temperature. Now, obviously, if that was lead, I could have melted lead, right? But if we're talking about most structural metals, iron, aluminum, copper, nickel, or titanium, they conduct heat away fast enough that you've got to put something on the order of 1,000 watts per square centimeter. Maybe it's 500 watts per square centimeter, but it's on the order of magnitude 1,000 watts per square centimeter in order to get melting, okay? So here, over at the other end, what goes on? When I get to above 1 million watts per square centimeter, what happens? Here I have too little heat. Over here I have too much. Hey, you know, this is not too hard to figure out, right? So here, if I'm at 10 to the 7th, you'll get vaporization rather than melt. Okay? I'm putting over here, when I'm above 1 million watts per square centimeter, I'm putting the heat in so fast that thermal conductivity of the metal is not high enough to diffuse the heat through the metal before the top of the surface reaches the vaporization temperature, and I basically just blow the metal apart. And that's known at 10 to the 7th watts per square centimeter as hole drilling. And I've already passed this thing around before, but you may or may not have paid as much attention to the holes, the air cooling channel holes in here, which are either laser or electron beam hole drilled. Okay, and some of these, if you actually look on the edge, you can see the holes where they cut through the holes coming in at a steep angle. You couldn't do that with a mechanical drill. Certainly not in that alloy, which is really tough, really strong. Yeah, well, and does it work that way? In terms of power density, yeah. Except the EDM is going to have a power density in here. we'll talk about that. But well, actually, we can talk about it right now. An electrical discharge machine is basically a little wire that just cuts its way by arcing through the material. You just run a wire, a continuous wire, spinning and this slowly moving in. So you can think of it as a bandsaw blade, only in this case it's a small wire, but instead of having teeth, it basically just has a voltage on it. It's in a cutting fluid, and basically just kind of has little arcs, and each little arc melts some of the material. Well, it turns out that EDM is going to be an arc which will typically have a heat intensity on the order of 10,000 watts per square centimeter. Now, the EDM arcs are very small arcs for very short duration, so they may actually be pushing up here towards 10 to the 5th watts per square centimeter. But this actually, this is not mine. This comes from, you have a paper by J.E. Anderson and Stracino on flames, and I actually took a course 27 years ago or something from Anderson, and this is his overhead, where he plots lasers and electron beams up here, arcs right here, and we'll talk about jet burners, but basically oxy-acetylene flames right here, and then propane torches and things over here. You don't have to worry about all these other things in here. You have a copy of this, I think, in your notes. In fact, I'm sure you do. He also plots the blackbody radiation temperature. Here, the blackbody radiation temperature is only 2,000, equivalent 2,000 degrees Kelvin. Well, 2,000. That's if, well, the surface is radiating away as much power as equivalent power of 10 to the squared watts per square centimeter. You can see over here, I'm getting to temperatures that'll melt virtually anything over here, and electric arcs will essentially melt virtually anything. Of course, lasers and electron beams will melt huge quantities of, or melt anything very rapidly. And that's the next thing I want to start talking about, is what is the efficiency of all this. But in any case, you can look at any welding and joining or welding heat source, fusion welding heat source, and it has to lie on this one-dimensional graph. It has to be on here. I sometimes point out that virtually any time anyone comes up with a new heat source, one of the first things they do is try to use it for welding. I may have mentioned that in the very first lecture, okay? Sir Humphrey Davy, when he discovered the electric arc in 1807 or 1805, we don't know exactly because you didn't have as much pressure to publish quickly back then, but he basically had two horizontal electrodes, and he pulled them apart, and this was, people just, Ben Franklin was doing electricity experiments with kites, right? And Michael Faraday, or no, Sir Humphrey Davy, Michael Faraday was back in that period too, but Sir Humphrey Davy basically had some Leyden jars, and so he had a fair amount of current on the order of tens of amps, and he brought two electrodes together, and then he pulled them apart, and he got a flame, an electric flame, between there, and it formed an arch, and so he called it an arc. He's the guy who invented the term arc, and it comes from an arch because the hot gases were rising and expanding and formed an arch between the two electrodes. Well, one of the first things he did when he talked to the Royal Society and the Proceedings of the Royal Society and explained his work was he said, well, he tried to melt two things, and he found he could melt things and weld them together, okay? Now, arc welding didn't become practical for another 70 years or so. It wasn't until the 1880s or so that arc welding became practical or possible. Anybody know why it took that long? It has to do with people named Edison and Westinghouse. You never had a power source. I mean, someone in 1850, where are you going to go plug into the outlet on your carriage? The horse just doesn't draw that much current, doesn't provide that much current. And in fact, there is a woodcut from a French laboratory in the 1870s where they have a whole bank of Leyden jars. Leyden jars is just a little electrochemical cell. They have a whole wall about the size of that wall over there full of these jars, and they have people doing electrical welding. Okay, that's the earliest known electrical welding. The patent for arc welding was given to a Russian scientist named Bernard in like 1883 or something like that. And it was really because people didn't have a source of electricity readily available until Edison and Westinghouse came along and invented electrical generators and started supplying power to industry. Before that, it was water power. And we'll talk some more about that later, but in any case, down here, you're not going to be very efficient because you're just barely putting the heat in fast enough to get the surface up to melting temperature, and you're going to lose a lot of heat diffusing into the metal. That's not doing melting of the metal, but just heating all the metal around it. And so typical types of efficiencies down here are going to be 2% to maybe 10% in some cases. Whereas over here, you're blasting the material, and if you only go in with 1,000,000 watts per square centimeter, you can make laser and electron beam welds. And in some cases, people have measured 99% heat efficiency. Basically, almost all the heat you put into the thing is going into melting. And whether you believe 99% or whether it's 97%, doesn't matter. It's above 90%. For typical arc welding, which is by far the most common, we're in the 30 to 70% range for heat efficiencies. Not terrible. Anybody know what the efficiency of an internal combustion engine is in terms of its input, you know, the thermochemical power of the gasoline versus the mechanical power that you get out of the car? Anybody know what the efficiency is? Yeah.
About 37.
37, that's pretty precise. I was going to say about 30%, but anyway. Depends on what car you're talking about, I'm sure, and how you drive it. It's the BMW, yeah. Okay. Going at 120 miles an hour continuous, right? In any case, anybody have an idea what the thermoelectric efficiency of a utility plant is, where you're generating electricity? You're burning coal or something like that, and you're a nuclear reactor, although that's not quite as relevant, because you're not talking thermochemical.
57 or 59.
Yep.
It was the gas turbine and steam.
Right. If you do what's called combined cycle, well, let me back up. When I was your age as a student, it was like 35 or 40%, maybe about 40% for the electrical. You know, if you went to electrical utility, you went to, what do we call it? Is it Boston Edison still? But whoever generates the electricity around here. And that was basically you burn coal, and how many watts of electrical energy do you get out of how many watts of incoming coal energy? It's only about 40% efficient. Today, it's 55 to 60% efficient. And what they've done, actually what happened because of the energy crisis, people started looking at how to push up the efficiency, and it's called combined cycle. You basically take the waste heat and you use it to do something else to get some, because the basic turbine may be up to 40, 45, something in there. Gas turbine is 40 to 45% efficient, whereas it was probably 35% efficient 25 years ago. So it pushes up, but it's very slow. But now they basically take the waste heat out of the gas turbine, and they do what they call combined cycle, and they run lower pressure turbines, or they use it. In one case, I know they were using it to preheat. They use the steam. It's low-grade steam. Low-grade meaning low-temperature steam, so you can't drive a turbine with it very well. But in one case, I know they were using it to recycle cardboard. They basically need steam to heat up the cardboard to turn it back into a mush so that you can remake paper out of it. And they were recycling paper, and they were using the low-grade steam from the gas. They had a gas turbine that then fed a steam turbine, and then the steam out of the steam turbine basically went to the boxboard plant, what they call the boxboard plant, to essentially help make paper. So they're actually combining industries together so that they get the maximum efficiency out of these things. Whereas in the old days, they used to just blow the steam up the stack and heat up the air and make it more pleasant for the birds in the winter. Anyway, so you have different efficiencies most arc welding, and frankly there's a problem in arc welding. You can go to the literature and you'll find numbers anywhere from 30 to 70%. There's a serious problem in how you define efficiency in an arc welding process, in terms of, you know how much power you have from the wall plug, but how do you determine efficiency in terms of just pure melting efficiency? It's sort of this whole area is a mess to look at in the literature because everybody's defining things differently. You also, as you go over here, obviously if most of the heat is going into melting, you're not going to have a lot of waste heat heating up the surrounding material, and then therefore what we call the heat affected zone, which is the material adjacent to the fused metal that has changed its structure. And I passed around steel welds before, that HY80 weld, and you can see a 2 or 3 millimeter wide heat affected zone on those arc welds. It's an area that heated above, in that case, 700 degrees centigrade, changed its crystal structure and transformed, and it etches differently afterwards. It also has a different microstructure, has different mechanical properties. So people are interested in heat affected zones. Sometimes they want to make them as small as possible, such as in welding most steel or aluminum, but sometimes they want to make them as large as possible, such as welding the chrome moly steels in nuclear utilities, because in that case the steels need to be tempered, heated up, not to melting again, but to an intermediate temperature. And so the bead, if you're putting a multi-pass weld bead on, you want the bead on top to temper the bead underneath. And so you want a big heat affected zone. It turns out over here, where you're wasting a lot of heat because it's a slow process diffusing, letting heat diffuse into the base material, you get a big heat affected zone. And over here, people say you get no heat affected zone. Well, that's wrong. And the reason it's wrong, if I actually look at heat affected zone width in centimeters, and I have this watts per square centimeter log scale down here, people basically look up here and say, gee, for the slow processes like oxy-acetylene welding or arc welding in here, I'm going and getting a much smaller heat affected zone. I can have heat affected zones 2 or 3 centimeters in width with something like oxy-acetylene welding. But it's going to be down on the order of a centimeter or less. Actually, it should be millimeters down in here, with arc welding. And people just kind of extrapolate that and say, well, it goes to 0. Well, does it go negative? I mean, you know, gee whiz. In fact, what happens, if you actually think about what happens over here, the heat affected zone at lower heat intensities is actually going to grow during the heating cycle. This is the, if I'm looking, put a thermocouple in a plate and I do a weld across there, traveling across there, there will be some temperature rise time. I reach my melting temperature up here somewhere, and then after I pass, after the heat zone passes, the heat source passes, I start to cool. Well, this heat affected zone is formed on the heat cycle, and this is formed on the cooling cycle. So this is 10 to the third to 10 to the fourth, and this is 10 to the fourth to 10 to the sixth. The heat affected zone is going to be formed by that cycle. So it turns out that over in this region, the heat affected zone size is directly proportional to the time that the heat source is present, whereas over in this region, the heat affected zone is really related to the width of the material that I melted, because that determines how much heat has to be carried out by cooling. If I make an electron beam weld and it's 1 millimeter wide, I'm going to have a narrower heat affected zone than if I make an electron beam weld that's a centimeter wide. They're both 99% efficient, but obviously one of them's got 10 times as much heat input as the other. If it's nearly 100% efficient in melting, but one of them melts 10 times as much material, it's going to take 10 times as long to cool. And that's going to grow the heat affected zone on the cooling cycle. And so I wouldn't say that it's more than once a year I go to a conference and hear someone talking about or read some journal article or something, and someone says, well, we use laser and electron beam because you can get rid of the heat affected zone. Well, the only material I've ever seen that didn't have a heat affected zone, I don't know if I mentioned this to you before, was once when I was at Lawrence Livermore National Lab, and these people was visiting one of my students who was he was a student here at MIT, but he was on loan he was an employee of Lawrence Livermore, and they sent him back here to go to do a thesis. And I went out there one time, and he was out there one summer, and I went out to visit him at his site. So I got a very nice tour. The only problem, it always kind of bothered me, every building, this Lawrence Livermore was where they designed nuclear weapons, right? And every building I went in, since I didn't have a security clearance, I wasn't there for that, I was just kind of on a friendship tour. Every building had one of these little kind of A-frame things they have for like cleaning the restrooms, you know, they put in front of the doors, and it said uncleared visitor in this building. Because I had to have an escort everywhere, and I was the uncleared visitor. And always, every time I looked at it, I thought, unclean visitor. I was, contaminated in some way. No, actually, probably they were contaminated. So anyway, but if I walked down the hall, I mean, people would walk ahead of me and announce that the unclean visitor or the uncleared visitor was in the building, and people would lock their file cabinets. And anyway, so they had me in a conference room, and they put this. They were interested, at the time we were studying fluid flow in weld pools, and they put this weld in front of me, cross-section of a weld, a picture, and they were asking me about some of the flow patterns in this weld, and so I was talking about, you could see some swirling from the microstructure in the weld, and so we were talking about it, and I noticed that there was no heat affected zone. And I said, what kind of material is this? And they kind of ignored me. And we kept talking about, and then I said, what kind of material is this? And they ignored me again. And the third time I said, what material is this? I've never seen a material that didn't have a heat affected zone. They said, oh, that's plutonium. So it was a cross-section of a plutonium weld. It turns out plutonium has a very, very low thermal conductivity. And so it takes a long time for heat to diffuse into the plutonium. This actually was an arc weld on plutonium. And it's more like a ceramic or even an insulator. It has lower thermal conductivity than many ceramics. And so the heat doesn't diffuse in a normal amount of time. And so it ends up with almost no heat affected zone. So for whatever that's worth, next time you're looking at welds on plutonium. So decreasing heat affected zone size, going from several centimeters down to millimeters, but it could be 1, it could be 10 millimeters, depending on the width of the fusion zone on heat affected zone size. Decreasing interaction time, obviously it's slower over here and shorter over there. It turns out the typical melting time here could be 10 seconds on this side, and it could be 10 to the minus 5 seconds over here, or, well, let's just call it 10 to the minus 6 seconds. I have seen melting with electron beams and lasers welds that are that short. And in the middle at arc welding, there is an interaction time that's on the order of 1/10 of a second. Now, 1/10 of a second response time. If you see a car in front of you slam on the brakes when you're driving, how long does it take you to respond to that? About 1/10 if you're really fast. Most people around 0.15 to 0.2. Over at the Science Museum, they used to have a little thing where basically you'd stand there and you watch this array of lights, and it would start the first light at the top would light, and then each one in succession. And as soon as you see the first light go on, you were supposed to hit a button. And it would time you between your first light and when you actually got the button pushed. And I used to be able to get like 0.17, 0.18 was kind of the best. Now maybe you can get 0.1, but if you can, then you really ought to go into some certain types of games, that like video games, betting and things like that. You don't have to have a computer to do video betting. You can actually go into a bar and you can do the George Washington nose game. Anybody ever played this? This is a game where one person gets their forefinger and their thumb all ready, and you can't touch George's nose but the other person is going to drop the bill, and if you can catch the bill, you can't reach down for the bill, right? But if they can get, it's a question of who buys the drink, right? So we got George's nose here, and now I actually do it pretty well. I've got a very good reaction time here. You want to try this? You buy. You were down way below George's nose, you still missed it. Why? If you calculate the drop time, it's about 1/10 of a second from George's nose up to here. And very few people can do it in 1/10 of a second. Now I can do it every time. Why? Because I actually have some pre-knowledge, right? However, we can up the ante, and we can do Ben's nose. You want to try Ben's nose? Let's do it this way. Ben's nose is shorter this way. He's not symmetric anymore, right? Now, there's a problem with this. I've done this in class before, and the student actually caught it. And that's because anyway, don't feel bad. The student actually caught it because I let go and I had some moisture on my hand and it stuck. That's adhesive bonding. And we didn't need sound for that, did we? No, we're back. We're back? Okay. In any case, there is actually a principle to this. It's not just for fun to tell you about George's nose. If I'm down here at Arc Welding and I want to control that weld puddle, I have to have very good response time. It's kind of like playing a video game. And when we train welders on how to arc weld, this is a manual process. Many places, well, some places will try to train a person to weld in 2 or 3 weeks of developing the skills. And they will start with arc welding. But if you go over here to Wentworth Institute, where they will give you a 2-year course in how to weld or a 1-year course in how to weld, you'll always start with Oxy-Acetylene, which is at 1,000 watts per square centimeter. Okay? And the reason you do that is the interaction time for the weld puddle in Oxy-Acetylene is on the order of several seconds. And so what a welder is doing with the heat source, they're moving that torch around to control the weld puddle. They're trying to fill up a seam. And if the weld puddle starts to move off to the right or the left or get too big or too small, the person adjusts the heat source. Well, clearly, if the weld puddle has a long time constant on the order of seconds, it's a lot easier for someone to do that. It's like when you first start out a video game, you don't start out on the highest level, you start out on the lowest level, right? However, if you go to arc welding, yeah, you can give someone a crash course in 2 or 3 weeks of arc welding, but they make really terrible looking welds to begin with because they just don't have the interaction time. They can lose the puddle. The heat will move the puddle to the right or become too big and burn through or lose the whole melt or whatever before they can respond to it. And what happens if you go up here to a higher heat intensity? There is no way for a human to be able to follow the process. And that means down here that you're going to have to automate the process, and we'll get to that in a second. What else was I going to say about this? I was going to say something else about decreasing interaction time. But in any case, that's why we start with the slower process. Oh, I was going to tell you the story of, this was 25 years ago. I'd learned to weld by arc welding. I was a welding engineer at Bethlehem Steel, and I didn't know how to weld because I had graduated from MIT, and we didn't know how to spell weld at MIT. They put me in the welding department. And so one day, after being there a couple of months, I went out to the technician and said, "Hey, can you teach me to weld?" And so he gives me, sets me up and starts me arc welding. So I learned on the hard way, where you start out on the highest level of the video game, basically. And then I came back here, and a few years later, this might have been a little over 20 years ago, I was walking through my lab, and a few of the students were sitting there oxy-acetylene welding. And I went over to look at what they were doing, and this was terrible. I mean, they looked like they were, dropping, and there was a dog walking down the street, leaving something on there. And I said, oh, well, let me show you how to do that. And I picked up the torch, and we put the two pieces of sheet steel together, and I put down a bead, and it was a beautiful looking weld bead. And I said, oh, okay, and I kind of told them how to do it. And I walked away. Well, they didn't know at the time, that was the first time I had ever oxy-acetylene welded. And the only reason I was able to do it was because I knew that the big problem in oxy-acetylene welding is there's a long interaction time, and don't try to go too fast, okay? And so I went very, very slow, and I was patient, basically. So that's the key. If you really go patient, if you go slowly, you can get and you're patient, you can learn oxy-acetylene fairly quickly, and then you can move up the scale by going to arc welding. I never did tell those students that was the first time I'd ever oxy-acetylene welded. Anyway, if you have decreasing interaction time, you're going to have increasing travel speed. Here it's going to be, you're going to have travel speeds on the order of 1/10 of a centimeter per second. And here you can have travel speeds on the order of 100 meters per second. Well, you don't usually do that. But when you get to these types of travel speeds, you really are going to have to automate that. Who could follow a seam at 100 meters a second? Only a robot, right? No human could move the torch along the seam or move the part in front of the torch at those types of speeds. So you're going to have to automate. If you have to automate, oops, that's the wrong one. Let's push them both up. That means that you're going to have to increase the equipment cost. And it turns out that you're going to have to go to robots and other things, and they cost money, numerical control tools and whatnot. It turns out that if I look at this, I can get in the business of an oxy-acetylene torch setup. I actually have a couple of them at home, and you can certainly get a simple one for $200 or $300. You can get a good commercial one with the regulators for the gas tanks and everything for on the order of, all the bells and whistles for $1,000. If I wanted an arc welding setup, I could buy a cheap one for home for $1,000, but really if I want to buy a good commercial one, I'm probably going to be closer to $10,000. And if I want to get a laser electron beam, I can buy a little laboratory laser electron beam for $100,000, but if I really want a big commercial one that's going to be able to do parts at a reasonable speed, and it's more than just the machine, and I start looking at all the automation that has to go with it, it's going to be $1 million. So you can change this watts per square centimeter to dollars per capital cost of equipment. Okay, going across there. And that actually holds pretty well. Inflation hasn't killed it for me yet because I'm on a log scale. I may die before it doesn't work anymore. But this comes from something I put together a number of years ago. But this is the capital cost of the equipment in dollars for the capital equipment versus the productivity of weld per second in centimeters. So you can get up here to 10 meters a second as a practical welding speed. Theoretically, you can get to about 100, but I don't know anyone who's doing 100 meters per second. I have heard of people doing something approaching 10 meters a second. I'll tell you what that is in a second. But down here with flames with low heat intensity, you're 1/10 of a centimeter per second, $1,000 cost of equipment. The arc welding, you can go a centimeter a second at $10,000 capital cost, and you can get laser and electron beam way up here. Now the interesting thing is resistance welding, when you want to weld sheet metal together and you basically come in with these 2 copper electrodes and squeeze the sheet, you can buy that equipment for on the order of $10,000 or $20,000 for commercial equipment in the automotive industry. And that equipment is substantially cheaper for the rate of welding that you can do with it. And that actually is one of the reasons, in my opinion. There's several reasons, and maybe even better reasons than this one, but this is at least a secondary reason why people use resistance spot welding for putting automobiles together. its speed, its productivity rate is high compared to its capital cost. And that's one of the key metrics in the automotive industry. People have been talking about using laser and electron beam in the automotive industry for years, but the problem is there's a huge increase in cost for the increase in productivity. Now, I remember back in the mid-'80s, there was a vice president at General Motors who really wanted Frank DiPietro. But anyway, he's probably been retired for more than 10 years now. But he spent $50 million of GM's money trying to put lasers into the production environment. And there are lasers in the production environment today, 15 years later. But one of his goals to the equipment manufacturers of lasers was to drop the cost of their equipment by a factor of 10, because that was what he was faced with by the beam counters, in terms of, we can't afford this equipment, it's too expensive, we can't run the numbers and make it work as an economical process. Now it turns out lasers got into production in the automotive business because they were put in as a research tool, not based on their economics. They knew that they were not going to be economical from a pure cost point of view of production, but they put them in because they just wanted to try it out, and they basically wrote the capital cost off as a research expense. And as they did that, they learned certain things about how to use lasers in production. And now in the automotive industry, we actually use lasers not for just assembling things so much, but what they did is they learned how to use lasers so that they now make what they call tailor welded blanks for the last 10 years, which has become a very important technology in lightweighting steel automobiles. If you're doing a formed part, you don't want the same thickness steel everywhere on that part. And so they actually will weld two pieces of steel, two different thicknesses together with a laser, because the only thing that's going to be able to have enough productivity to do that many linear inches of weld for the automotive industry is going to be high productivity laser electron beam. They'll weld those things together, and then they will form the part, and you'll have a part of two different thicknesses, thin where you want it and thick where you want it. Okay, so they have tailor welded blanks. They also have blanks that are not just rectangles. When you stamp out sheet metal from the steel mill, it comes in a big roll, and it's going to be rectangular or square. You can have square if you want. That's just a subset of rectangle, right? Now they actually can make these, two different rectangles sticking together, and so they actually save on scrap cost. So that's been one of the big things in the last 10 years is tailor welded blanks, because of the very high productivity of or high speed of welding of lasers. And they don't use as much electron beam certainly for automotive assembly, because electron beam has to go in a vacuum, and we can talk about that later. But another thing that's important in all of this is the depth to width ratio of the weld pool, or the ability of the heat to penetrate and cause melting. Over here, you're going to have a weld pool on oxy-acetylene that might look like this. It might have a depth to width ratio of 1/5. And over here, you can have these holes that you drill, and typically you might get 10 to 1, 10 times as wide, or 10 times as deep as it is wide. They have made welds at the Welding Institute in Britain that have an aspect ratio of 200 to 1. A 20-inch thick sheet of aluminum, or block of aluminum, welded with only a 1/10 of an inch wide weld zone, 200 to 1 aspect ratio of that weld. That was just done to say it could be done. The problem with doing something like that is if I actually wanted to make a real part, and I had something that was this thick, and this is not 200 to 1, in fact this is probably only 20 to 1 or something, and I put a weld in there that looks like this, if I'm off by just a little bit, I'm going to miss the joint. I can miss it angularly, I can miss it this way. There's no flexibility in the fit up when I go to a super aspect ratio. So even though I can get 50 to 1 without much difficulty in electron beam, I can't use it in a practical sense. So 10 to 1, maybe 15 to 1 is about the highest you'll ever see people go. And the last thing here is increasing production volume requirements. Obviously, if I'm going to start paying $1 million for my capital equipment, I'd better have either a lot of something to put through there, or I have to have a very high value added part. And who has a lot of something to put through there? The automotive industry. And who has very high value added parts? The aircraft industry. Okay? And if you look at lasers and electron beams for welding in systems, and I have the data somewhere in my office, typically they might sell 100 of these systems a year around the world, maybe 200. But 90% of them go into the automotive for high volume or the aerospace for high value. In the automotive business, they're going to run these systems at 80-90% duty cycle. There's not going to be a lot of downtime for maintenance. It's too expensive a piece of equipment. And they're the only people who have the capability of putting enough material through there to make it economical to run the part. You can't use lasers and electron beams in shipbuilding. People have used it thought about it for years. And they might be able to do it in one part like a panel line or something like that. But you get out there in the ways, you know, where the building, assembling the whole ship, you don't need to make welds that fast. And you can't afford 10 times the cost of capital equipment to be able to make them faster when you don't need to make them that much faster. The forming and everything else and fit up takes more time. In the aerospace industry, the electron beam welders may only be used 2 to 5% of the time. But you're making parts that are worth $70,000 a piece, and if you screw it up, you're going to be very unhappy. So it turns out there's certain types of welds that can't even be done with arc welding, but you can make some very specialized welds with very specialized shapes, and gives you certain capability that's very valuable for lightweighting structures in the aerospace industry. So you don't care if the equipment's just sitting there idle most of the time. You want the capability of the material, and you're willing to pay the premium because you have high value added parts. So if you look at it and you actually see where the equipment is sold, it's sold into aerospace and automotive. Now there are a few others. There are things like bimetallic strips that people weld. They take a piece of carbon steel band and a piece of tool steel band, and they weld the two together to make a bandsaw blade. And this is done in western Massachusetts in this electron beam welding process. So 2 strips of steel coming in, one a cheap steel, a spring steel, to give stiffness to the bandsaw, the other a high-speed steel, which has got a highly alloyed molybdenum, chromium, and all this other stuff, very expensive steel that's only maybe 1/8 of an inch wide, just the height of the teeth on your bandsaw. You come in, you weld those together with an electron beam. It has to be done in a vacuum system, but the rolls come off in the air, go through a little feed through into the vacuum system because it's just simple strip geometry. Goes through, welds, and comes out the other side. Might be doing it half a meter, or let's say a meter a minute, okay, or a couple of meters a minute. You need, because you're going to make a lot of this length, you need some reasonable speed, but you don't need, you don't need a lot of expensive material. And you then grind, after you finish the weld, you then grind everything smooth so it's nice and flat again, and then you cut the teeth, hopefully on the right side, so that you get good properties. And so there you actually make a part that costs twice as much as just a plain steel one, but it has maybe 3 or 4 times the life in cutting materials. So you can get your premium cost, and the whole thing is cheaper in the long run, even though you went through an extra process. Yep. No, and that is probably a meter a minute. I mean, well, maybe it's a couple of meters a minute. It's not super fast, but I mean, if you're making bandsaw blade, even a meter a minute, 360 meters an hour, or even if it's 2,000 meters an hour, you only have to go so fast. You couldn't do that with an arc weld, though. That's still faster than you're going to ever get with an arc weld. Okay, I'll see you. Actually, there's class next Wednesday, but I'll be wherever I'm going to be. I'll be back Thursday and Friday. And the week after that, we're going to go every